In previous sections, we took a look at power series, and we did take a look at Taylor polynomials. In this section, we're going to specifically take a look at how to find Taylor and Maclaurin series in the closed form as well as the series form. And so we're going to first look at these things called Maclaurin series, and we're going to be able to find a Maclaurin series as well as the interval convergence. We're going to find a Taylor series for a given function, as well as the interval convergence, and then we're going to use series to approximate a value, which we may have done in previous sections as well. Let's start off with one of the easier types of power series, which is a Maclaurin series. And a Maclaurin series is essentially a Taylor series that's centered at 0. In other words, we just keep finding derivatives of the function, substituting 0 back into that derivative, and then just multiplying it by x to the n over n factorial as n keeps increasing in integer values. And so this is the expanded form, okay, in a pattern. All right, so each time we just keep going through 0th derivative, first derivative, second derivative, third derivative, evaluating at 0, multiplying it by x to whatever that derivative is, and then dividing it by n factorial. So these sorts of problems, we're looking for patterns to be able to get to something of this form. All right, so that way, if we wanted to find like a 20th degree polynomial, we could just stick 20 in for n and then be able to get out what the polynomial is going to be. So let's take a look at several examples of this, okay? And be warned that some of these problems do take a long time and they do require some intuition of patterns. So we have this function f of x ln of 1 plus 5x. And what we're going to do is we're going to find the first 4 non-zero terms of the Maclaurin series. Then we're going to find the Maclaurin series using summation notation. And then finally, we're going to find the interval of convergence, which we've done in previous sections. Okay, so first thing we're going to do is we're going to find some derivatives. And then we're going to evaluate the function or each of the derivatives at 0. Okay, so I'm going to call this n. And that's going to be like 0, 1, 2, 3. If we need another one, then we'll go up to 4. And these are just going to be the derivatives. So this is going to be fn of x. Okay, so the 0th derivative, remember, is always going to be the original function, ln of 1 plus 5x. Now, the first derivative is going to be pretty easy. We just use a chain rule. So that's going to be 1 over 1 plus 5x times 5. Okay, remember we have a chain rule because we multiply by the derivative of the interior function. And another way to write this is going to be 5 times the quantity of 1 plus 5x to the minus 1. And that's going to help us to avoid using a quotient rule. Second derivative is going to be negative 5, 1 plus 5x to the minus 2 times 5, or negative 25, 1 plus 5x to the minus 2. Third derivative is going to be 10, or I'm sorry, that's going to be 50, because we're going to multiply this negative 2 times 25. So that's going to be 50, 1 plus 5x to the minus 3 times 2. Or times 5, excuse me, from the derivative of the interior function. And that's going to give us a positive 250, 1 plus 5x to the minus 3. All right, now we're going to substitute 0 back in. So the nth derivative back at 0. And the reason we're doing that is because if we look at the formula, that's something that we have to do for each of the terms in this Maclaurin series. Okay, so if we substitute 0 back in, for the first term, we get ln of 1 plus 5 times 0, which is ln of 1, which is 0. All right, so unfortunately, this term we're not going to use. It doesn't contribute to the sum. However, for the second term, we have 5 times the quantity of 1 plus 5 times 0 to the minus 1, and that's just going to be 5. As we keep doing that, what we're going to notice is these are going to cancel out if we substitute 0 back in for x, and we're going to be left with the coefficients. Okay, so that's negative 25. This is 250. And because we're asked to find the first 4 non-zero terms, we're going to have to find one more derivative. Okay, so this is going to be the 4th derivative. And so If we multiply these, that's going to be a negative 750, 1 plus 5x to the minus 4 times 5. That's going to be negative 3750, 1 plus 5x to the minus 4th power. And if we substitute 0 back in for x one more time, that's going to be negative 3750. All right, now we have these, and these are going to be the terms or the first 4 non-zero terms in this series. Okay, so the way we're going to write this, we're going to have our series n equals 0 to infinity, fn at 0, x to the n divided by n factorial. All right, or in other words, that's going to be f at 0 plus f prime at 0 x plus f double prime at 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial times x cubed. And then finally, we're going to need the 4th derivative to get 4 terms out of this. 4 factorial x to the 4th. All right, now, f at 0, if we substitute back into that 0th derivative, that was just 0. Okay, so if I write this out, that's going to be 0 plus, and we're just going to go right down the list and substitute these values back in for the 1st, 2nd, 3rd, 4th derivative. Okay, so this is going to be, remember we had 5 up here, and then negative 25, and then 250 and 3750. So this is going to be 5x. Okay, so we're just substituting 5 in right here. And then this is going to be negative 25 over 2 factorial x squared plus, remember we got 250 over 3 factorial x cubed. All right, and then finally we got this negative 3750 over 4 factorial x to the 4th. Right. And so finally, if we simplify this just a little bit, all right, and I'm going to simplify this, and then we can write it into the series form. This is going to be equal to 5x minus 25 over 2x squared. Right. Now remember, 3 factorial is 6, okay, because that's going to be 3 times 2 times 1 for 3 factorial. And then 250 divided by 6, they both have a common factor of 2. So that's going to be 125 over 3 x cubed. And then finally, 3750 divided by 4 factorial, right? I believe that these both have a common factor of 6. All right, so if we take 4 factorial, remember that's 3 times, or 4 times 3 times 2 times 1. It's not going to simplify completely, but if we just use our fancy calculator here, 3750 divided by 6 is going to give us 625. Okay, so this is going to be plus 625 over 4 x to the 4th. All right, now these are the first 4 terms, okay, as we're writing this in. Okay, so remember, it asked us to find the first non-zero terms of the Maclaurin series. So this would be like term 1, term 2, term 3, and term 4. All right. Now, for part B, we have to find some sort of series for this. All right. And what's helpful is to maybe rewrite and see a pattern as to what's going on. And so I can rewrite this as 5x over 1 plus 5 squared over 2x squared plus 5 cubed over 3x cubed plus 5 to the 4th over 4x to the 4th. And that would just keep going on forever. Now, 625 is 5 to the 4th. 125 is 5 cubed. 25 is 5 squared. All right. And I want you to notice that each of the powers of x and the power of 5 are congruent to one another, but also take a look at the denominator. Okay, so if this were like an n, and you could think of 5x as 5x to the 1st, and then obviously I've made some copy errors on the signs. All right, so this should be a negative and this should be a negative, and this should be a negative. So sorry about that. What we can do is we could just go ahead and write this into a series form. All right. And so the series we would get, ignoring the signs for right now, that's going to be the series. I'm going to start at 1 to infinity, and that is going to be 5 to the n x to the n over n. Okay, so I want you to notice that this is like 5 to the first, so we have a 1, 1, 1, and then a 2, 2, 2, 3, 3, 3, 4, 4, 4. Now, the only other thing that we have to worry about is making sure that we have alternating signs, because it is an alternating series. And so what I'm going to do is I'm just going to make this -1 to the n, and then I'm going to substitute 1 back in to see if that gives me the first term. All right, so when n equals 1, this would give us 5 to the first, x to the first, over 1, and then -1 to the first, which would be -5x over 1. And that's not correct, okay, because we want a positive. So because we want a positive, what we're going to do is we're just going to rewrite this as n equals 1 to infinity, 5 to the n, x to the n over n, -1 to the n plus 1. Right? So the last, and this would be our series form. Now, the last thing that we have to do is we have to find the interval of convergence. All right. And to find the interval of convergence for this one, we're going to have to use the ratio test for this. All right. So let's hold on to this. All right. I'm going to refresh this so I have a little bit of room to work with. Well, that doesn't help because that just rotated it. And we remember that the series that we just found to represent this function was the series n equals 1 to infinity, 5 to the n, x to the n over n times -1 to the n plus 1. And so we're going to find the interval of convergence by using the ratio test. All right. And so to do that, we're going to take the limit as n approaches infinity. We're going to plug in n plus 1. So 5n plus 1 x n plus 1 divided by n plus 1, and then -1 to the n plus 2. And then we're going to divide all of that by 5 to the n, x to the n, divided by n times -1 to the nth power, or the n plus 1th power. All right. Now remember, that has to be less than 1 for this to be convergent. All right. Now the good news is that even though this looks ugly, we can simplify this a lot. Okay, so what we're going to do is we're going to take the limit as n approaches infinity. And remember that these are negligible for us, okay, because when we take the absolute value, those are just going to cancel out. So anything that has a -1 to an n power, the absolute values are going to cancel those out. And then we're going to group like sort of expressions. So we have 5 to the n plus 1 divided by 5 to the n. Okay, so notice we have this and this. And then we have x to the n plus 1 divided by x to the n. And then finally, we're going to have n over n plus 1 if we simplify this. Okay, and it has to be less than 1. All right, so basically what I did was just multiplied by the reciprocal of this, just like we did in previous sections, and then simplified it just to save time. Or this is going to work out to be the limit as n approaches infinity of 5x. Okay, so notice we have 5 to the n and n, those cancel out. We're left with 5, and then x to the n and n, so that leaves us with x, and then n over n plus 1, less than or just less than 1. And now we can go ahead and take the limit of this. So that's going to be the limit as n approaches infinity of 5x n over n over n plus 1 over n, less than 1. And then finally, we can go ahead and just apply the limit to all of these, or actually just this one. All right. The first one is just going to become 1. All right. So remember, n over n is just going to be 1. This is going to be 1. And so we end up with 5x times 1 is less than 1, which implies that the absolute value of 5x is less than 1. Now, if we wanted the radius of convergence, we would just divide by 5, all right, and we would get that absolute x is less than 1/5. And this would be the radius of convergence, okay? So just trying to remind everybody of how to get the radius of convergence. But to get the interval of convergence, we're going to have to break this up into a compound inequality where we have negative 1/5 less than x less than 1/5. And then what we're going to do is we're going to substitute it back into this original series and then try to simplify this, okay? So we're just going to test it at both of the endpoints, all right? And if we do that, let's start with x equals minus 1/5. And so if we do that, we're just going to substitute 1/5 back in for x here. And that's going to be 5, or series, excuse me, 5 to the n. So n equals 1 to infinity. So that's going to be 5 to the n minus 1/5 to the n divided by n. And then we're going to multiply that by minus 1 to the n plus 1. Right? And so if we want to try to find the interval or the radius, or to determine if that converges or diverges, we notice that these are like powers of n, all right? And we can go ahead and rewrite this as n equals 1 to infinity. We could write this as 5 or minus 5 over 5 to the n. Let's rewrite this as minus 1 to the n times minus 1. Okay, so just breaking off this 1 here, and then that's going to be divided by n. Right? Or, in other words, that's going to be the series n equals 1 to infinity of minus 1 divided by n. Right? And the reason being is because we can see that this is minus 1 to the n, and when we multiply it by these two, they just cancel out, and we're just left with this minus 1 that's going to come down here. Right? Now, clearly, if we were to go through, it's not an alternating series test, but it's a p series. All right, we could factor the negative on the outside. All right, and so we had the opposite of n equals 1 to infinity of 1 over n. This is actually the harmonic series. All right, so this is going to be harmonic, okay, which means it diverges. All right. Or you could say it's a p series, all right, whichever way. Now we still have to do the other side where x is equal to positive 1/5, all right? And this one's going to give us a convergence, okay, because this is going to be our series n equals 1 to infinity, 5 to the n, 1/5 to the n. And then we have that minus 1 to the n plus 1 divided by n. Let me erase this, make it look like a real 1/5. And then 5 to the n times 1/5 to the n, we can rewrite that as series n equals 1 to infinity of 5 over 5 to the n minus 1 to the n plus 1 divided by n. This is just going to become 1 to the n, which just becomes 1. And so this is going to become the series n equals 1 to infinity of minus 1 to the n plus 1 divided by n. And this is an alternating series. And so what we're going to do is we're just going to go through and use the alternating series test. All right. If I say a sub k is just going to be the absolute value, or the absolute value of a sub k is going to be 1 over k. All right, so we just get rid of the absolute value. And we know that this is going to be decreasing. Okay, so if k were 1, 2, and 3, and this would be a sub k absolute, so this would be 1 over 1, 1 over 2, 1 over 3. And so it seems like it's decreasing. Okay, and that's good. Okay, so that's the first part. And then remember, for the alternating series, we just have to take the limit, or the alternating series test, as in this case, we have 1 over k, right? So we're just going to take the limit as k approaches infinity of 1 over k, and that's going to be equal to 0. Okay, so it is going to converge at n equals 1/5, or x equals 1/5. All right, so finally, we can get to the interval of convergence, and finally, probably after 20 minutes, we're done with this problem. So it looks like that the interval of convergence, okay, so remember, we go back up here. Remember, we had from negative 1/5 to 1/5. It was convergent at 1/5, but it was not convergent at negative 1/5. So for the interval of convergence, that is going to be open parenthesis negative 1/5, closed parenthesis positive 1/5. All right. So a lot to do in that problem, okay? But nothing that we really haven't done before, except maybe finding the series in the closed form, okay? So we'll take a look at another example of this, so that way we can be certain that we have a backup example that's a little bit tougher than the previous.